Good afternoon, everybody. This is Rovina here, Marcom Officer at Palladian, and welcome to the Palladian webinar series. Today we have Prashant Verma, the Senior Practice Manager Secure Testing at Palladian, who will be taking up a session on securing secure browsers. Prashant?
Yes, hi.
Yeah, Prashant.
Good afternoon, everybody. Yeah. So as Rovina has mentioned, this afternoon we have securing secure browsers as topic for the webinar. So at Palladian Labs, we do conduct research on multiple different security testing aspects and security testing platforms. So I'm the part of practice team here who is into the service development and improvisation. So this topic, securing secure browsers, is a result of the internal research conducted against the standard products called secure browsers. Okay. So our agenda for this webinar is to see the threats at browser, and we'll see how secure browsers as a solution address these threats. As in the secure browsers, by the name say that they are secure, so the threats are supposed to be secure. So, but our research proves that some of these security aspects in secure browsers are still hackable. So we'll see the secure browsers hacks next. And we'll conclude with the discussion on how to further strengthen the security of the secure browsers, as in how to fix these hacks which are possible. So effectively, it is about securing the secure browsers. So before getting into the topic, let us quickly look at what are the insecurities, or effectively what are the threats at the browser. So these are the threats which are displayed in the screen is some of the threats which are applicable to the browser. So here I'm not presenting a comprehensive list of browser threats, but I'm presenting a threat list which is claimed to be secure by secure browser. So threats in context of secure browsers. As we see, compromised browser executables. So every browser has installation files, it has executables from where the application, which is effectively the browser application which is launched. So if, what happens if the browser executable itself is corrupted, the browser itself is corrupted. So we'll see how to corrupt secure the executables in terms of secure browsers. What happens if the browser components itself are corrupted? So like Microsoft browsers or the browsers running on Windows operating systems, they have different components, processes, DLL files. So how about the corrupted browser components? So like if these DLL files start controlling the traffic, then many things can be edited within the browser itself. We'll see this again in detail. And the acceptance of fake SSL certificates. So man in the middle attack, wherein a proxy is set in the browser, and then effectively traffic originating from the browsers are intercepted in that middleware proxy by introducing the certificate of the proxy in the browser. So secure browsers, as such, they have controls implemented wherein they do not allow just any SSL certificates to be accepted. So we'll see again what can be done here to bypass this. Then we will further see malwares which can read and modify the browser memory space. So browser, since it is an application in the operating system, it would have a temporary memory space within the RAM or within the temporary memory. So that temporary memory space tends to store information like the passwords you enter in the browser. So till the time browser is open, a password is bound to remain in that temporary RAM. So we'll see how malwares can interact in case of secure browsers as well to read or modify those. Then we'll see the third-party plugins. So a lot of the users, including you and me, use some of the third-party plugins. We import these plugins in the browser. So these help us in different aspects of the application usage or different aspects of the browsing. So again, in context of secure browsers, third-party plugins are not allowed to be loaded. So we'll see how we can bypass this, or how we can still get a malicious plugin loaded into the secure browsers. Finally, web application attacks, since browser run multiple web application in them. So like cross-site scripting attacks, wherein a script is sent by attacker to the user to steal session cookies or to do some malicious activities. So effectively, it is the JavaScript which is playing the notorious game here. And the phishing websites in context of, again, web apps, wherein a fake website is allowed to be open in the browser and user innocently passes on his details to the fake to the faked website. We will see again in context of the secure browser. Okay, so before getting into how these threats are secured or they are bypassed in a secure browser, let us see quickly what is a secure browser. Secure browser as such is a commercial product, especially it is considered by banking or financial institutions. Well, government and military organizations do use some form of secure browsers or secure browsing solutions. But since these are commercial products, mostly it is considered by high business banking applications or high business banking organizations where security is of the prime concern of top executives. Okay, so secure browsers and secure browsing solutions. There is minor difference between the two terms. Secure browsers as such is a specifically developed browser which is claimed to be secure, while secure browsing solution, it tends to bring in a solution on top of the existing browser to secure it. So let us again see this in further detail in the next slides. So these secure browser or browsing solutions protect against various attacks like man in the middle, man in the browser attacks, keyloggers, phishing and DNS. So this is a claim by the secure browser or browsing solution. The PPT as such or the webinar as such is focused on bypassing these secure claims of the secure browsers. Okay, so secure browsers type. So like basically three types of secure browsing solutions we have seen. One is like secure browser itself. So the browser itself would open by clicking on its own executable, and the instance opened up would be a secure browser or a secure instance. While second bullet, as it tells about, there are secure browsing solutions which secure the existing open source browser, like Mozilla and Chrome are the available browsers. So if you install a secure browsing solution on top of your Chrome or Mozilla, so now your Chrome is a secure browsing solution, or it's a secure browser. Okay, then secure browsing solutions which are hard coded in an external media like a USB. So you plug in a USB stick to your laptop, and then the USB stick is write protected. You cannot edit, you cannot tamper the executables. Only thing you can do in this pen drive is just to launch that browser, that secure browser. Okay, so some of the underlying functionalities of the secure browser and how do they claim to secure it. So effectively, sandbox environment is the technique wherein each instance of a secure browser is separate than the other open instances. So sandbox, like no interaction with other instances. Okay, so what would effectively this mean? This would mean like applications, processes, or malwares running on one sandbox could not access the data related to the other instance of the browser. They cannot interfere at all. So if my target banking app is running on one instance, while the attacker's malicious application is running on the other tab, wherein the JavaScript tends to steal the information from this. So being a separate sandbox, it segregates the two environment. So the JavaScript from one instance cannot access the JavaScript of other instance. So effectively bringing in the security. Okay, then secure browsers have a nice feature wherein they claim non-tamperable browser installation or component files. Okay, so when we talk about installation files, executables, DLLs, so then these are actually non-tamperable. For example, we discussed the case of hard-coded USB drive. So the USB drive has the installation file. You just have to click there to install and run the application, but you cannot really tamper it. So that's again a nice security feature. But we'll see again how to effectively bypass this. Okay, monitoring of browser executables. Now these browser executables are loaded, and then a process monitor tool can see what are the components of the browser which are under current execution. Okay, so now these secure browsing solutions, they have another privileged process associated with these browser executables. As in, there are, let's say, three processes, process A, B, and C. If a malware is trying to hook into process C, so this monitoring of browser executable, this process would flag off that there is a tampering or there is some malicious activity going on in the executable C or the loaded process C. So it can be configured to block such kind of execution. So again, a very good feature by secure browsers. Okay, then secure browsers manages certain whitelist. So this again are to safeguard against different threats. So whitelist of websites is managed. So this effectively would help in flagging off a potential or a possible phishing website, because that is not present in the whitelist. A user should not be connecting to it. Okay. Then it also maintains a whitelist of SSL certificates, as in we discussed man in the middle attack, wherein a proxy certificate can be loaded onto the browser. So if browser has all the possible SSL certificates loaded onto its store, it's present in the whitelist. So this proxy certificate, which is not in the whitelist, cannot really connect the users. Effectively, it is targeted towards preventing against man in the middle. Okay, so then we see protect against the memory space. So as we see, the memory space has a lot of data like passwords. Then you have keyloggers, which can tamper into what are the key strokes which the user is trying in his browser. Then we have screen capturing attacks, wherein a screenshot of the current browser screen is captured and taken. So secure browsers implement solution to protect these. And finally, there is non-whitelisted third-party plugins. So the third-party plugins which organization allows to use are present in the whitelisted store, and those which are not to be allowed or not to be used by enterprise users are blacklisted, or effectively they are not whitelisted. Okay, so this is like a quick picture on the security of secure browser. Now let us see how these secure features can be attacked. So what are the attacks on the secure browsers? Okay, so these are 10 different attacks which we are going to see next. Man in the browser, 3 different scenarios: DLL proxying and proxying the Windows DLL and function hooking. We'll see all these in great details. We'll see the data stealing from the browser memory. We'll see how the data, how still plugins can be installed, how keyloggers can still capture the keystroke, how the monitoring of browser executable, which was preventing connections from malwares, can still be bypassed, and such connection can be made. We'll finally see screen scraping, a technique to steal the data from the data of the screenshots stored in the system. Then we will see the redirection from the host file. So most of the secure browsers also claim to protect against the redirection attacks. We'll bypass that as well. Okay, so getting into the first attack, DLL proxying. So we discussed in a normal browser, we can do man in the middle by exchanging the certificate. So similar attack is tried in the secure browser, and it is actually possible via man in the browser attack. So here we need to figure out a specific DLL which is related to the network communication made by the browser, HTTP or HTTPS connection. So if we can tamper into such DLL which is making the connection, we can control the network traffic. So without making a fake SSL certificate of proxy to be accepted at the secure browser, we are still able to tamper and view and modify the data from the browser. So let us see how this is possible. Okay, so we create a proxy DLL which replaces the actual DLL. So this actual DLL is the networking DLL, network connection DLL of the secure browser. So effectively data which is intended for the original DLL, which is networking DLL, is sent to the proxy DLL. Notice that, note that proxy DLL is a DLL created by attacker and original DLL is the browser's DLL, which is networking DLL. Now proxy DLL has the capability to view and tamper data before it is being passed to the original DLL. So we view or tamper data via proxy DLL. So next let us see what is there in the DLL proxy. Okay, so the key trick here is to identify the original DLL or to identify the DLL which has to be proxied, or to identify the DLL which has to do with the SSL implementation, or which has to do with the networking communication HTTPS. Okay, so we'll take a case wherein we had targeted WinINet DLL, which is again networking DLL or used by the current browser. Okay, so effectively for conducting man in the browser attack using DLL proxying technique, what we did is WinINet.dll is the original DLL used by the browser, and WinINet-_.dll is the original DLL used by the browser, which is renamed, and WinINet.dll is now our proxy DLL. And additionally we had to write an iexplore.exe.manifest file. So this manifest file and all these three, original DLL and the proxy DLL, all these three files are stored in the program files directory of the Internet Explorer section. So the manifest file directs the browser not to use the system's default WinINet DLL, but it sets the priority that browser should be using WinINet.dll, which is proxy DLL. Okay, so what it means? So it effectively means that the traffic sent by the browser was captured by the proxy DLL, which was set higher priority, and a file called file.txt is created. So this file has data dump of all the traffic which was sent by this browser. So post request sent to some application where user ID is test and password is test. So user ID, password and the HTML source code of the browser application is captured in the file.txt created within the browser directory. Okay, so now people must be thinking what is inside this DLL proxy. Okay, so this is a snapshot of the proxy DLL which we have written to capture the traffic. It effectively captures some of the functions, as you can see, IP buffer, DW number of read, IP number of bytes read. So these are the functions which are used by the original Windows DLL for the network communication. So we have hooked into these functions and we have printed using fprintf function. We have printed all these data traffic into the file called file.txt. So which we had seen in the previous screenshots. So that particular section of codes directs the data to be captured and written in the text file. So from here it can be edited. The traffic being sent out from the secure browser can be edited. Okay, so this is another slide which actually tells us about the intricate functionalities of the proxy DLL, wherein the specific function, what IP buffer, why IP buffer is of interest to us, because it really points to the data which we have to write from the buffer to the text file. So what we have displayed is the capture of the data. Similarly, you can write functions to tamper the request. For example, similarly a proxy DLL can be written to tamper the data from a username test to, let's say, username ABC, or any other kind of variable. So the whole point I'm trying to make is, it is quite interesting to see that although man in the middle attack via SSL certificate exchange is not possible in case of our secure browsers, but using the man in the browser technique, we can still replace the DLL by creating a proxy DLL and still capture the traffic. Okay. Then there is a modified version of the same attack, which is proxying Windows DLL. So now in the previous version of the attack, we had effectively tampered a DLL file which was used by the browser for the communication. So that was a browser component DLL which was used by Windows, but there can be a modified technique where we can directly tamper the Windows DLL itself. Okay, so Windows DLL, ws2_32.dll, this is a Windows DLL. This is responsible for the network connections originating out of the Windows based applications. Okay, so here we target the system's default DLL. So effectively we rename it to something else, and as per the previous technique, we create a proxy DLL for ws2_32 and we set a higher priority for that as well. And then the traffic starts flowing through the proxy DLL, wherein we can read and edit it. Now there is a challenge in this system, in this method of doing, so which is why we prefer the previous method over this method. So the challenge as documented here is that the Windows self-defense mechanism, which prevents against its own system DLLs getting tampered. So effectively Windows do not allow its system DLL to be tampered. To safeguard against this, Windows creates its own backup copy of these DLLs and temporarily and then intermittently it restores the tampered DLL from the original DLL from its backup location. So although an attacker or we have created a proxy DLL, but if Windows replaces it frequently, will not be able to proceed continuously or smoothly with our attack. So yeah, so this is a challenge with this approach, but effectively this is also a possible approach, though first one is a better workable approach. Okay, so the third attack we should see in the secure browser category is function hooking, which is the most common attack technique employed by the malwares. So we have seen Zeus malware and other banking malwares wherein they also use function hooking technique in the browser. Zeus was specifically focused to steal two-factor authentication token. Most other malwares also do the similar technique of function hooking. Okay. So in our attack, we would try to decide on which function to hook. There are multiple open source debuggers like PYDBG is one of those debuggers. So let us see a target case wherein NSP4.dll, again a component used by the browser, is targeted, is hooked into. Okay, so effectively NSP4.dll is responsible for network traffic encryption and used by the most of the secure browsers. What we did is we wrote a script which was monitoring the functions which were loaded into our browser processes. So the secure browser was not allowing any fake processes to be introduced. So this particular browser, when it saw that a fake process or something like a malware is trying to interfere with the loaded process, it used to drop the connection, or it used to alert the user that a possible malware attack is trying to inject into the browser. So then user could itself terminate the connection, or solution can automatically terminate the connection. It depends really on the solution. Okay, so here we tried to bypass this security of the secure browser by terminating the monitoring process itself. So the process which was alerting the user or which was terminating the user session when a fake malware was trying to interact with the browser, we killed that process itself. And after killing this monitoring process, we loaded the malware into the secure browser. Okay, so this is a screenshot of Python debugger which we had used. So via this screenshot, here we were using a secure browsing solution which was securing Firefox itself. Okay, so it has successfully hooked into the process which is running on at this particular memory address, and by terminating the process ID 16880. Now, so when you use the debugger, you would realize what these processes are. So 16880 is the process which was securing the browser. So we terminated the process with the process ID 16880, means we terminated the monitoring process itself before the malware was hooked into the network encryption DLL. So effectively, using function hooking technique, we hooked into the encryption process of the secure browser. So now when we are into the encryption process, we can code the encryption differently, or we can decrypt, read the traffic and re-encrypt it. So effectively, the encrypting process of the secure browser is now in our control using function hooking method of the man in the browser attack category. Okay, so let us move on to the another technique. So another technique which we discussed was the security of the secure browser, wherein the browser memory segment is not readable to the third-party apps, or not readable to the anyone else, or sometimes they fuzz the data, or do some kind of encoding into the data so that even the stolen data is not readable to the person who is stealing it. Okay, so how we bypassed it? We use memory scanning technique. We know that in a 32-bit Windows system, the memory ranges is from 00 to 027 FFFFF. Okay, so we wrote a script which is monitoring this particular address space of Windows system 32-bit, and to this script we provided a specific search string. In the current context, we were testing an application which was sending a user ID, wherein the user ID has the variable name as being displayed here, FLD login iUser ID. So we are scanning the entire memory range for a particular text to see whether user ID or associated password is being stored or is being recoverable in a clear text format, because the secure browser was claiming that it cannot be read. Okay, so this is the code section from the memory scanning script written by our R&D team. So it is scanning the entire range. It is searching for the string FLD login user ID, and then it is printing out 15 previous and 75 next characters related to FLD login user ID. And in the memory we had found this. So this is the snapshot. So we were able to find out the user ID and the password as the user has typed in the browser from the browser memory of this secure browser, whereas the browser solution is claiming that the memory segment is not readable. Okay, so next attack category in the discussion is injecting malicious browser plugins. Okay, so we talked about a little bit about this, that the plugins which can be loaded in the secure browsers can be specified by the organizations. So which plugins which are allowed by organizations admin are whitelisted. They are whitelisted. So the non-whitelisted or malicious plugins which can hack or tamper into the users' applications are not allowed because they are not whitelisted. Okay. So how did we inject a malicious plugin in this secure browser? So 4-step process as is written here. So we wrote a script that monitors the system for a specific process. So wherein it was the browser specific process to be monitored in our case. So the process which was monitoring the loading of such plugins, the process itself is terminated or is killed. Now the process which was preventing the plugin to be loaded is killed. So we have won the one half of the battle. Now there is no monitoring, we can load our plugins. Now there was quite some challenges to load the plugins in originally running instead of the instance of the browser. So as part of an attack, what we did is we created a pre-saved profile of the browser. So this pre-saved profile already had a malicious plugin loaded. So this again would require some kind of man in the browser insights to launch this attack, because you need to save a browser profile having a third-party plugin loaded into it. So now let's say when the Firefox with the pre-saved profile boots in the safe mode, boots even in the safe mode, the extensions are loaded because the monitoring process is killed. Okay, so here is the screenshot depicting what we did. So if you notice, there are two parts. One is like path F where Firefox is originally running. So this Firefox F is hard coded in the F drive, which is a pen drive wherein we cannot tamper it, while the current profile being loaded is from C drive. So this C drive Firefox profile is where a third party plugin is preloaded. Notice that we had still run the pre-saved third party loaded profile of Firefox from the F drive while the instance was in C. This is possible only when we terminate the process which was monitoring the loading of such profiles or such plugins. Okay. So next two screenshots here display the difference in the load of the Firefox. If you notice, there is no plugin here, and if you notice the second screenshot, there is a plugin which is depicted by icon S. So this S icon plugin is loaded in the current as part of the current saved profile. So effectively, the secure browsing solution or secure browser has been bypassed by injecting a third-party plugin. Okay, so the next attack in this category is keyloggers. So keyloggers, again, as we all know, these are the programs which tap into the keystrokes made by the user. So the secure browsers, they claim to protect against these as well. So in our study, we saw that some of the browsers are secure and some are insecure. There is a chart later to tell more about this comparison between different secure browsers. But the browsers were claiming that they add noise to the data, so that the keystrokes are not recovered or not stolen by these keyloggers when the secure browser is in place. So we had typed in this two-factor authentication token, and there is a search window also wherein we had typed the search string. So these two strings we have typed in. So ideally these two shouldn't have been captured by the keystrokes, by the keyloggers as part of the keystroke capturing, but since we were able to inject into the keylogger function, we did recover that in the crude format. So the screenshots show that two-factor authentication, search string, username, password, everything is capturable by a keylogger. Okay. Next attack again in this category is bypassing of the monitoring which is implemented for the browser executables. So we discussed a specific category of secure browsers wherein the browser executables as such are being monitored by the browsing solution itself, so that the things they are not injectable, they are not tamperable. So we wrote a script which can kill the browser process monitoring itself, so that the killing the process monitoring itself would make the browser executables vulnerable for all other attack categories wherein in process injections function hooking, all these things are possible. So that further control on the browser can be made, or the user session can be hooked into by the malwares. Okay, so here we specify, here we employed a specific technique wherein the Firefox.exe application, which is the protected instance of the secure browser, was being monitored for the name. So we renamed it to Firefox. We removed the first F. We renamed Firefox to Firefox, and then it was surprised to see that Firefox.exe is running without protection. The monitoring process is still monitoring Firefox.exe while the actual secure browser is running through Firefox.exe, for which there is no monitoring. So this way we bypassed the monitoring of the browser executable Firefox.exe. So the screenshot displays the same thing, wherein the process, the child process of PID 1168 was terminated. So this 1168 was Firefox.exe monitoring. So the other instance of this screenshot, which shows that running Firefox.exe instance without any protection or without any secure application against it. So the process is Firefox.exe is loaded currently with PID 151544, whereas 1168 process is terminated now, which was the original Firefox.exe. So again, an interesting attack vector to bypass the secure browser security. Then, man in the middle attack category, the very first thing which we discussed, the proxy certificates being exchanged for doing MITM, for listening to the SSL certificates, SSL traffic. So herein they maintain a whitelist of SSL certificates. So which is why the, let's say if you are using Burp proxy or a Charles proxy or a Fiddler proxy, so these certificates not being in the whitelist, we are not able to connect to the secure browsers. So effectively the traffic from the browsers did not reach to this proxy. So as such, there is if there is any deviation from this whitelist of SSL certificates, like a fake Burp proxy certificate coming in, either there will be no response, there will be no connection for the end user, or there can be an error displayed by these browsing solutions saying that SSL certificate blacklisted. Okay, so now it is good to see that when these MITM attacks by exchanging the SSL certificates was not possible, but still employing the man in the browser technique of proxy DLL, which we saw as a first case in this webinar, we can still listen to the, or we can still tamper the SSL traffic using that proxy DLL technique. Okay, so other attempt from our side was screen capturing, screen scraping, which is the act of gathering visual data on user's screen, capturing the snapshot of what is being displayed on the user's browser. So these snapshots are stored in the browser memory section, and then in case of some of the browsers, we were able to get into these as well. Okay, so last attack in this category which I would like to tell now is redirection against host files. So some of the secure browsing solutions, they claim to protect against DNS related attacks, wherein attacks like DNS cache poisoning, which rely on typing some particular DNS and getting redirected to something else, which is like poisoned cache of a DNS. So here we had tampered the host file of the Windows system. The host file, as you all know, contains host names to IP address mapping. So by tampering the entry in a host file and using a secure browser, we saw that we are still able to redirect Windows users of the secure browsers to the fake websites as we have tampered. So this way a DNS related security can still be bypassed. Okay, so we had talked enough about the browser related attack and the security features of secure browsers and how those could be bypassed. So let us now focus on how to secure the secure browser, which is the prime agenda or prime lesson for this webinar. Okay, so this is a case study of 4 different secure browsers or browsing solutions we have come across. So like the vulnerability status of different browsers against different attacks we had tried. So a big picture or the lesson from this is MITM attacks by exchanging SSL certificates that we had found safe in all of these 4 browsers. While doing the same thing, while doing the same SSL interception using proxy DLL, that was vulnerable in almost all of the browsers. While one specific browser was protecting the Windows DLL by the Windows system, wherein Windows inbuilt feature itself was not allowing the smooth capture of data, so that was found to be partially safe. Then we see that the function hooking is also vulnerable in most of the browsers. If you notice the browser lead, which is terming most of the attacks as safe. Okay, so this specifically is a browser which is being run on write protected USB, so which was not really possible to hook into, or where the memory space being present in the non-readable USB stick was not accessible. So for the keylogger, so it actually prevented against most of the attacks. While you see sensitive data in the memory, so we scanned all the memory ranges and searched for a specific text. So that was found to be vulnerable in all of these 4 browsers we had included in our study. Okay, so recommendations to secure the secure browsers. Proxy DLL protection, we saw that we could write a DLL which can tamper or read the data. So how do we secure against that? So if we maintain a whitelist of DLLs, as in what are the current DLLs which are allowed to be loaded, what are the current DLLs which are supposed to be loaded, and if we periodically check for the DLL list of the loaded DLLs, we would come to know what are the fake DLLs which are loaded. So that way we can detect an attempt like something which is made by proxy DLL. So such connections could be dropped or flagged up to the user not to connect. Similarly, there can be another technique called checksum validation of DLLs. So the original DLL for which we have created the proxy DLL would have a checksum which is different from the fake DLL which is proxy DLL. So the checksum would differ, checksum validation would fail. So a browsing solution can be developed in a way to terminate such cases where checksum validation fails. Then we saw function hooking protection. Then we saw function hooking as a technique to bypass or to terminate the original function and still load the malwares. So we can protect against such function hooking by using ACLib, like libraries like ACLib. So this is like open source library, but there can be many open source library or commercial libraries as well developed to effectively monitor or to debug or to trace down such kind of hooking attempts. So a new function hooking or terminating the existing process can be detected by such debugging libraries, and in a way they can protect against function hooking. So if they can detect, they can flag off a message, or they can code, or the solution can be coded to terminate such connection. Then we can also implement function hooking protection by not allowing the browser processes to be run independently. What this means is, in an example, we had run firefox.exe by renaming it as firefox.exe. So if we are not allowing such kind of process running directly, that also would protect against such hooking and termination of the processes. Okay, Then in context of keyloggers, so all the keyloggers, most of the keyloggers, they work by hooking into set Windows hookx function, which is a function related to the key strokes or key events. So for this event, if there can be some kind of monitoring or hooking or a debugging which immediately flags off that such function is being employed by some application which is interacting with the browser. So this would flag off or terminate such connections. Again, this is expected to be a good protection against keylogger. So the keystrokes can be prevented if such attempts to the function hooking of set Windows hookx can be flagged off. Then talking about data protection in memory, we saw that all the 4 browsers which we have studied, we were able to scan the data and read the data from its memory space. We were able to recover passwords to factor authentication tokens. Okay, so there are functions like malloc, calloc, which has to do with memory allocation and memory release. So effectively, these functions should be used to free out the memory space, to zero out the memory space when the browser instance is closed. So the browser is closed, passwords or the data which was stored is freed out, or it is just zeroed, 000, or fake data is inserted there. So even if in such cases the memory is read by some script or some fake application, what they would get is effectively some zeros or some fake data. Okay, we also saw that third-party plugins can be loaded into the browser by using a saved profile of the browser which was stored in some other path. So how can we protect against this? Because we were able to load the third-party plugin from the profile, from the saved profile. So why not block the saved profile parameter at all in these secure browsers? Do not allow a profiling to be done, or do not allow a saved profile instance to be loaded, or allow the profile parameters to be loaded from a valid path only. We saw 2 paths. Path F drive was the original drive, while C drive had the saved instance. So effectively, if you allow it to be loaded only from F drive, that C drive instance containing the third-party plugin is not loaded. So you further secure the secure browser for this particular check. Then we see how to safeguard processes which are monitoring browser executables. As we saw, there are some monitoring processes which are monitoring the browser executables. So we terminated these monitoring processes, these privileged processes, then our secure browser instance became as if it is a normal browser instance, because the monitoring process itself was killed. Okay, so how can we secure it? We can one option to secure it is by parsing the header values in the PE file. So now what it means. So PE file contains the browser PE files contain the known file signatures, and it has the header values of the known files. So effectively, we know what are the known files, what are the expected PE files, what are the expected header values in the current PE files. So we can parse those values. So any surprise header value appearing here is a possible malware which is trying to kill the monitoring process. So again, such process should be terminated, and there can be a separate monitoring functions implemented to parse these header values of PE files periodically. So periodically you detect if any malware is trying to hook into the process, or is trying to kill the safeguarding process of the, or trying to kill the privileged processes which are safeguarding the original browser executables. Okay. So effectively, there is a secure browsing solution which can ensure where there are various program DLLs loaded. So these checksum validation on the program DLLs can also let us know about the fake DLLs which have been introduced as part of the man in the browser attack category. So if checksum is validated, such kind of DLLs again can be dropped or cannot be connected to. Okay, so this is what I had for this afternoon, wherein I wanted to cover on secure browser attacks and the security measures as to how to prevent against the security implemented by the secure browsers. I hope I was able to clearly tell the browser related attacks and was able to make some of the recommendations to further strengthen the security of the existing secure browsers. Okay, so we are now open to take up any questions or any doubts which you people may have. Okay, so Jamal Qasim is saying that the presentation was very good. So thank you for the feedback, Jamal. We'll see that the copy of the presentation is available. Okay, so there is another user comment wherein the user is asking for wanting to know more information about non-executable browsers. Well, non-executable browsers, not really, because all browsers have executable files. So all browsers have executable files. So there is nothing on non-executable browsers. Another question which is asking about, can the default browsers like IE, Chrome can never be used for secure transactions? Well, for the default browsers, there are some security plugins available, some of the mechanisms which users can use themselves to secure it. For example, there is NoScript plugin available for Firefox. So if you use that NoScript plugin, no JavaScript can steal data from your Firefox browser. There can be other things like some of the antivirus also prevents tampering into the browser components which are related to the operating system. So these operating system can flag a potential process hooking. So these are solutions which users can deploy or employ on their own. But secure browsers are way above those, because these are the browsers which build in security within the browser itself. For the default browser, so IE is a commercial browser, but Chrome and Mozilla, they are open source. So there are solutions to secure these browsers itself. So if you refer back to the presentation, there were a couple of instances where I have bypassed a particular attack in the secure version of Firefox.exe. Firefox.exe renamed to Firefox.exe. So this was open source browser but was secured by a commercial secure browsing solution. So it is not that the default browsers can never be secured. There are secure solutions which user can use on their own, but the commercial products of secure browsers, they invest quite a good amount of security mechanisms to secure the users. So the presentation was targeted to bypass those as well and to further make recommendation to secure the commercially secure the secure browsers. Okay, the keylogger attack. So keylogger attack, all the keyloggers are working by using the Windows functions like WinInet function, which is like socket hooking, so which is related to the keystrokes typed in by the user. So these keystrokes can be captured by the use of that particular function. So elimination or isolation of the keylogger by secure browsers have to monitor such kind of function usage related by any of the process which is loaded by the secure browser. But if the question is in general, let us forget secure browsers for a moment, how to still isolate the keylogger. So this is what most of the antivirus or malware monitoring solution try to do. So they also try to monitor that this keystroke function, if it is being used by a particular application, that is a possible keylogger. So they try to eliminate such kind of calls. Okay, so there is another question which is asking me about my feedback on a specific query browser. Actually, we do not want to publish a data vendor wise, which is why I have refrained during this presentation by taking the names. So even in my comparison chart, I have used browser A, B, C and D while presenting the picture, because the idea of the presentation is not to comment on security or insecurity of a specific browser, but the general message is how to further secure the existing secure browsers. So unfortunately, I'm not able to answer this. Okay, another question coming up is there a requirement to supply secure browsers to customer? I do not know of a mandatory requirement to supply a secure commercially secure browser to customer, but financial organizations would like to supply this to their most privileged customers, like top 10 business icons of a country. So a bank would like to supply such solution to them. It's only for the super privileged customers, wherein bank would like to invest this kind of amount. Okay, another question is about how to avoid usage of portable apps. So portable apps, as I understand, these are the apps which are running from the external drives, external USB or external CD drive. So their interaction from the application which is running within the secure browser, again some sort of monitoring function or a debugging function which is periodically checking into what is allowed interaction with the browser, what is allowed and what is not allowed. So if my browser running from C drive and external portable app which is running from F drive is trying to connect, a monitoring app can monitor such connections and can flag or can block such connections. Okay, another question asking about Citrix to publish the browsers. So if you talk about normal browsers where access is provided using the Citrix as a solution, it definitely tries to bring in security, as in the entire access is privileged, entire access is over SSL. So SSL MITM attacks encryption related attacks, privileged access related attacks. So those kind of attacks are protected by the solution itself. But again, secure browsing solutions, since these are commercially developed solutions, these are way above that. For example, a Citrix, a browser, a normal browser published over Citrix, that might not prevent against memory screen scrapping or memory stealing attack or a keylogger based attack. So yeah, secure browsing solution is above that Citrix security over the existing browsers. Okay, another comment wherein more information about screen scrapping is asked for. Okay, so screen scrapping is a technique to capture the screen and store it in the system drive. For example, currently thank you screen is being displayed to all the participants. Okay, so in context of the browser, if you are on a page wherein you have entered your 16-digit credit card number, CVV number or expiry date, so a screen scrapping attack would try to steal such a snapshot from the browser. So these snapshots are taken and stored in the C drive, D drive, or somewhere in the within the browser memory space. A screen scrapping would try to steal such memory snapshot. So a .jpg or a .png file is the stolen part of screen scrapping. So what we can expect to find in this JPEG or PNG screenshot is the 16-digit credit card number if it is not masked, or the CVV number and the expiry date. Or effectively, I am trying to say that whatever is being displayed in the browser screen and that has been captured as part of the screenshots can be stolen via screen scrapping attack. Okay, examples of secure browsers are like a secure browser from Novell, Edge browser. Then you have query browser, which another user has just asked in another question. Okay, so we have so far answered all the questions. Is there any more question? Okay, there is another question about does browser support two-way SSL? So I guess the question is about secure browser. So I'll interpret it as does secure browser support two-way SSL? Okay, so for this I need to check the specification of different secure browsing solutions. As we are talking about 4 to 5 different products, so some of these may still support it if you go and check the specification of these. So they can support it by importing the SSL. So we discussed about whitelisting of SSL certificates. So whitelisting as a feature of importing SSL certificates is available in some secure browsers. So if SSL certificates can be imported, so I understand two-way SSL can also be supported. But to give a precise answer, we should be reading the product manual of these secure browsers. Okay, so another question or comment which is asking me for the browsers which were tested and displayed in the comparison snapshot. Again, I would apologize here. I would not like to take the names of these 4 browsers wherein the case study was presented, because our target is not really the browsers. Our target is to tell about the vulnerabilities in the secure browsers and how to further secure it. Okay, query browser is one secure browser which one of our participants has reminded us. Okay, so another question asking about, from the mentioned 10 attacks, which attack is most vulnerable to all browsers? So this particular screen of this slide says it. Sensitive data in memory was the one which was found to be vulnerable in all the cases. Plus proxy DLL, which has the most impact. The proxy DLL which can steal data, even though SSL certificate protection is there, we can still tamper and edit the SSL traffic. So this I would term as most sensitive, and was found in most browsers as well. Okay, then we have replied to all the questions we have received. I would like to thank everyone for joining this session this afternoon. Hope we had a good learning session.